Okay, let's talk about Gaussian mixture model. For this tutorial, I'm going to just use a synthetic data set so we can actually see how GMM work. And then we're going to use AIC and BIC to figure out the optimal number of clusters because as you know, for GMM, we have to give it how many clusters we want. And so AIC and BIC will create an elbow that it will show that what will be the optimal number of clusters. Okay, let's get it started. So I'm going to import NumPy again because we want to create a synthetic data set. So we need NumPy for that reason. And I'm going to say as NP again because I want it to be shorter. So when I'm using it in the code, I don't need to write NumPy. And then we're going to import matplotlib, again matplotlib, matplotlib.pyplot is for visualizing the data. Again, I'm going to, and then the next thing that we want to import, which is in sklearn.mixture, it is our Gaussian mixture model. So it is Gaussian mixture. You want to create the synthetic data, but you want to test it with the clustering algorithm. Okay, so when you want to do that, there is a very good library which is called MakeBlub, and it is in sklearn datasets. So when you're using that, your data set is actually going to be look like blobs everywhere. So when you want to cluster it, you can see, and then you can change the shape and how spread these blobs are. But generally, it's a very good thing for testing how your clustering model did. So from sklearn dot datasets, I'm going to import make blobs. Okay, so let's make our data set. Make a data set. So this data set, I'm going to say I want a number of samples that okay, I'm gonna go with 700. And then I'm going to specify how many clusters I want. I want my clusters to be, let's say 7, 2. And again, I'm going to set a random state because I want my code to be reproducible. Equals to, I'm just going to say maybe 32 this time. I'm going to say x is equal to make blobs. Actually, this one. And then we have n samples. Number of samples is going to be 700, which we said, which we defined it as n samples. And then I'm going to say what are how many centers I want. So my centers are going to be n clusters. So that just shows where your clusters are going to be shaped, that where the density of your clusters are going to be. So the points that are created are going to be scattered around the center of the cluster that you are choosing here. So I'm going to say I want 7 different clusters. So basically what it is that the density of the data is not going to be the same everywhere. I think you get it. So that's that. And then again, we're going to set, this is an interesting one. I'm going to set a cluster STD, which is standard deviation. And what it does is it will tell how close together or how far away, how dense our data is going to be. And you will see, we will change it and you see how it makes the difference. So I have cluster STD to 1. And then I'm going to create a random state again for reproducibility, and I'm going to set that to 32 as well. Again, you can choose any numbers. It doesn't really matter. So now I'm going to create 2 variables. So I will get my scores in there. And based on, and then when you plot it, you can see which value is going to be the best number of clusters for you. So if our AIC and BIC do well, we have to get 7 clusters. Since I want to get a list of AIC and BIC, like I want to give different number of clusters. For example, I would say cluster D's, using 2 data points, or cluster these using like 10 data points. Sorry, uh, cluster these using 1 cluster, or cluster these using 10 clusters. I have to give a number and then I will get a score, AIC and BIC score. So for that, I'm going to create a loop. So I'm going to set my range from 1 to, for example, 10. Now I'm going to set the parameters of my GMM. So GMM is equal to, going to Gaussian mixture, and then the values that it wants from me. What is the number of component? I think it's like, yeah, so n components. For n components, I'm going to set it to n because it's basically the clusters. Like it says how many clusters you want GMM to create. Random state for reproducibility again, so I'm going to set it to 32. And then I'm going to fit this. We're not going to transform or anything like that because I haven't said anything about that yet. But when you want to train your model, you just use fit. And then X, because now we are using our data set to see how well it's going to work. Okay, I'm going to append my score here. Since I'm going to plot each one of these values from the arrays that we got here. So since I set the range to from 1 to 10, I can again use the same thing for my plotting. So this is 1 to 10 for both AIC and BIC. And then, so right now, BIC is going to be blue and AIC is going to be red. So I got an error here. And for that, I just had to add a Y here. And the reason for that is because it says that you have only one D here. I have one dimension, which is X, but it says that it is required 2 dimensions. So I'm going to do X and Y. Now I'm going to create a scatter plot. What a scatter plot does, it is going to show where your data is located. So each one of these plots are different. I think we should talk about each one of them later. But for now, scatter just shows where the data is located. If you're looking at histogram, because when you're looking at normal distribution, that is a histogram. It's not where the data is located, but it shows how many of each data are there. Like for example, when I think the most common one is like the IQ score that you see, the bell curve. The people who score 100, they are the maximum number of, because there are so many people who score 100, like 100 is the norm. And then if you are lower or higher than 100, you keep the number of people keep decreasing. So don't be confused that why do they not look like bell. For scatter plot just shows where the data is actually located. So see, we are not doing hard clustering, but we are doing soft clustering. That means that one point in data can belong to multiple clusters. So that is why when we are looking at the label, it looks like a gradient. So this is very interesting. Um, I'm going to show you what's happening. So the number of clusters that I chose was 7. But when we are looking at the score for the number of clusters, okay, so the way that you're choosing the number of clusters is based on the lowest score. Okay, so we are looking at the lowest score, but after a certain point, the different number of cluster doesn't make that much difference. Like for example, from 5 to 6, the difference is way lower than when we were coming from 85 over 8,500 to almost 7,000. So the difference keep becoming less and less. And so since it is not making that much difference, you don't really need to um, create more clusters. So here it seems like 4 or 5 are going to be optimal, because after that it's just going to be almost in a straight line, and at one point it's going to be even worse. And it's very interesting because I set the number of clusters to 7, but it doesn't seem like the 7 is the best fit here. Now let's look at the data set and see why that is. Okay, so that is why, because this area, these 3 are very close to each other. These 2 are kind of close to each other. These 2 are further away. So I would say our AIC and BIC should have taken this as one cluster. This is 2, 3, 4, 5. So 5 is something that is okay, but also it might have considered these two as one cluster as well. So it can be one, two, three, four. And then let's look at this again. So yeah, four is the optimal. Five is a little bit better than four. And then after that, for six and seven, it just doesn't make any sense to have six or seven. So let's change our STD because I believe the reason we're not seeing the clusters very well, it's because of standard deviation. Now, if I go to zero point 0.5, we were at 1. Now I'm going to 0 0.5. You can see they're going to be very distinct. So now I have to get 7 clusters, which is 1, 2, 3, 4, 5, 6, 7. So now we have a clear 7 clusters. Now let's look at the AIC and BIC. This one have to show that 7 is the optimal number. Um, yes, look at this. So we are going down, down, down until we reach 7. 7 is the optimal here.